Hey, it says I'm live right now. Okay, now I fixed it. Finally. My phone really wants me to look at it. Okay, alright, so the last one was not streamed, but we got to this point where we're just going over some stuff. Mainly, I'm going over this so that I can explain it back to myself before tomorrow. See if I remember any of this. I haven't looked at it in about a week. So, we need to find, at this point, we know this. We know parts of this because the CPs go away. Delta T total is actually equal to the TO in, or 1, minus TO E, or makes it 2. So we know this one. We don't know this one. And if I remember correctly, the way we solve that for that is using some pressure and temperature ratios. All right, let's see what my professor did. So we went through, I said 524, she said 523, let's go. So we found that, we did that the same. Okay, so whirl velocity stator, I did not do that yet. So VU2, so what we're talking about here, if I remember this correctly, we're going to be looking at that one, and then this one, and then that one. So VU2 and VA, so I'm going to do a different color, see if I can do red. So this one is actually, boop, 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 boop. This is VU2. And then down here, technically, is VA. Because this and this are equal. And then we also were given alpha 2, which should be, do green, should be right here. If I remember that correctly, so that should be, going this way, so that's what our tangent, TOA, TOA, opposite over adjacent, our opposite over our adjacent. So this would actually be tangent of alpha 2 is equal to our opposite VU2 over VA. See, so that's where she's getting this. I actually have to write it down because I want my brain to remember it. Okay. This we'll use later. We won't use later, actually. I lied. This is what we're using it down here directly. So we solve for VU2. So tangent of alpha 2 is VU2 over VA. Rearrange this to find VU2 is equal to VA times tangent of alpha 2, where VA is equal to 600 feet per second times our tangent of alpha 2, which is 70 degrees, thus giving us 1648.5 feet per second. So there's no whirl at the rotor exit, so it means it's completely, there's no boundary separation. Everything's perfectly fine as that air comes out of there. Next, we're going to use stage work. This is actually our Euler formula. Delta E is equal to this. So VU3 is equal to 0, so we don't need that. Our CP times delta TO stage is equal to 5. So we're actually solving for something else, because this is, we're solving for delta TOS all down here. So where did I leave off at? 523.6. Excuse me, which is our U velocity, you mean, times our VU2 minus 0. We don't need that, so VU2 is our 1648.5. Now, multiplying these two together gives us this feet squared second squared. That's a huge number. 863,477 feet squared second squared. She breaks this up into two things. This is CP, but this is our conversion. These are two conversions, so this is what the gravity constant, and 778 I think is the BTU. It's a BTU conversion. Anyways, you have to do this and then divide all that, because I want to bring this CP over here. I usually put it all together so I can just put it in my calculator, call it a day. But this is easier. So I can just put it. But what does this give us? So realistically, we have our BTU. I think I can find. That's not what I wanted. Get that out of here. Conversion factors. Okay, so I'm gonna go back to blue. 1 BTU, that's our conversion. 1 BTU is equal to 778 foot pound force. So realistically, what we're looking at in CP is in BTU per 1. CP equal to whatever it is, it's 0.24, but it is also in BTU per pound mass Rankine. So we have a BTU per pound mass Rankine times our foot pound force times 32.2, and that is our GC, gravity constant, which is actually pound mass foot per pound force second squared. So what are we doing here? So our BTU, what are we missing here? Why is our BTU going away? Oh, duh, 1 BTU. That's what it is. So this goes away, 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 this goes away. We have, at the end of this, we are given foot squared, second squared, Rankine. So if you divide, so if this is down here, And this actually goes to the top. We know that. And then foot squared times square, or divided by foot squared, goes away. Everything checks out. I need to remember those conversions. Where's my... There it is. Excuse me. Okay, so all of this comes out to our delta TOS for the stage is equal to 143.6 degrees Rankine. Now we still need our total. So overall, we're going to use this property where our TOE for the stage and TO1 is equal to the pressure at the exit, stagnant pressure at the front, and then our gamma minus 1 over gamma. K, gamma, same thing. I like gamma. I'm a gamma kappa guy. But this is what we're looking for. We do have this. We were given this. We were given this, and we know all these. So TOE is equal to 2160 Rankine times our 14.7 psi over 140 psi. Those units cancel, and we have a 0.4 over 1.4, which always comes out to about 0.286. That's correct, right? Yeah, 286. $1239.8 Rankine. So now we can figure out our total, which is equal to our, just for the stage, we have our in and our out, giving us 920 degrees Rankine. So this is from our earlier talk where right here, delta H, and we know that the number of stages is delta H over delta H. But also, we have to know that there is a efficiency, because it gave us 86 for the, where's the, here, stage efficiency. So we have to multiply that stage efficiency right here, F times the total. So we have our 86% times our 920 times the stage, which we found way up here, right there. So 5.5 stages, which you always want to round up because we don't want to miss out on those stages. It gives us 6 stages. This is where things get hectic. So blade height. So this comes from our triangle. I'm going to draw our triangle again. This goes down here. This one goes down to here. This one goes here. This one goes here. These are all triangles. Vectors. Okay, I'm going to use red. So what are we looking for? We need V2 because we're going to use it later, which solving this backwards would be so nice. So blade height comes from our area. Dude, you have to know where you're going before you actually solve some of these things. So the final calculations that you can use are, that's our, God, where do we go from here? A2 is actually equal to 2 pi r h. 2 pi r mean h. Area 2. I believe this is specifically for, goodness, I'm gonna need to look for that real quick. Is this axial flow? Degrees. Hold on, I'm looking for it. I'm looking for areas. There's a breakdown. It's a great breakdown where it states the different areas for each rotor and stator. Maybe that's chapter 6 and 7. Oh, is it right here? No. This is a multi-stage action flow gas turbine. We don't know if it's an impulse or a reaction. That's super cool. Blade design. I'm looking. Don't kill me. Okay, actually, I can show you what I'm looking at right now. So, application of Euler's. Yeah, here's some stuff. It's not exactly what I was looking for. This is one of the values we can use for later, but darn it, man. There is a wonder if we can look up blade height. Let's see. I spelled it wrong. I didn't. My goodness, so many text messages. No, that's not what I wanted. Getting distracted. Huh. Odd. Really? Only... No, I don't want to look in sticky notes. Oh, turn sticky notes off, please. Okay. Anyways. Is this the same problem? It is the same problem, but solved differently. The solution is much different. This is not. Is this the PDF? This is the PDF I'm using. Okay, cool. Anyways, we're solving for V2 to get to T2 to get us to P2. So we're solving for velocity at the exit. We're looking for temperature static, pressure static, so that we can get to our density, thus giving us our A2 via mass flow is equal to rho 2 A2 VA. Yep, there it is. So it's this line right here. So V2, T2, P2, rho 2, A2. Crazy. So much math. So when we're looking at this triangle, we're going to look at our cosine alpha 2. So alpha 2 again is this angle right here. Alpha 2. Boop. And what we want is V2. Sorry, alpha 2 is also this one and this one. Adjacent over hypotenuse. Yeah, this is V2, I think. Hold up. This ain't right. Something ain't right. Final formula sheets. That's W2. V2 is this long one. So realistically, V2 is equal to this entire one. So it says alpha 2 is 70. My dog's asleep. Because this one right here is V2. This is the one we want. And we're only given the flow angle at the stator exit A2 is 70 degrees. 70 degrees is also equal to beta 1. But VA, where are we getting this from? So cosine alpha 2 is, oh my gosh, adjacent over hypotenuse. And so this should be the hypotenuse. So we should be using, this is U though. Should be this one and this one. Unless this is, I'm dumb. I'm dumb. This whole thing is alpha 2 right here. Right there. Because alpha 1 is this one. Beta 2 is this one. I'm so dumb. Yeah. Alpha 2 is equal to beta 1. Beta 1 is actually this one. Cool. So equal. Okay. So that's where we're getting that. When in doubt, chat it out, man. Okay. So, erase all this. I'm gonna redraw that because I want to know. So like this one. That's one triangle. This triangle. There. So this one is V2. This. Which is our W2, can't use that one. So it's got to be this one right here, which is VA. This one right there. Okay, got it. All the way across. Hold on. Delete this. Delete that. Cool. So this one right here. There we go. That's what I'm looking for. Alpha 2. This is my alpha 2 I'm using to find V2 and VA, because VA is the adjacent over the hypotenuse, not the opposite. Done. Oh my gosh, dude. Yeah. Nothing like doing trigonometry half asleep, make you feel like an absolute dummy, dude. Absolute big old dummy. Okay, I'm done. I'm done talking about this. God damn it. Okay, we have our velocity. We're gonna move on. What do we need to find? We need to find our temperature. T2. This actually comes from our. This comes from our delta H, or not delta H, but our H equaling CP times T. So that means we can have our T is equal to TO minus V squared over 2 CP. And these can be 1, 2, 3, blah, blah, blah. So we don't know this. We know our T2 because our T2 is 2160, which is our total temperature we're looking for. In this reaction, our T1, TO1 is equal to TO2. See if I can find it real fast. Our Moe diagram. 2, 3, 4. 2, 2, 2. There we go. TO2 is equal to TO3. HO3. Well, that shouldn't change. H doesn't change. Maybe that's not the correct way of looking at it. So stagnation, static, dynamic pressure, total enthalpy changes. That's where we get this from, though. Maybe that number is incorrect. I don't know why it's T02. Maybe in relation to the beginning of the stage. Anyways, this is our highest number. I think this should be different. I think this should be the lower one. But we just found our velocity squared. Or our velocity, then we can square that one. Gives us our T2, and then after we found our temperature, we're looking for our pressure. We can use the pressure relationship here. Stagnant pressure over static pressure over stagnant pressure. And then use the temperature relation here. Remember not to flip your gamma signs. I always have these set in my calculator. I don't know if anyone else does this, but K divided by K minus 1 is always, for me, 3.5. So if I have temperature, well, okay, if I'm applying it to temperature here, this becomes 3.5, always. Like, I just leave it at that. And then vice versa for the other one. So now we have our pressure. Then we can move on to finding our density. And we were told in the beginning of the question to look at this as ideal. Since it is ideal, we can use ideal gas law. P is equal to rho RT, baby. And we know what our density units are. They should all come out to that. How far off? How far from 0.128? What's the difference? Yeah. I think that's what she told us right here. Like, she gave it to us, but also we can calculate it. It should be the same. Since everything's the same, it's ideal. Anyways, now we can use our mass flow to change it all around. We have this, we have this, we have this. Now we need this. And there is our area using our blade height formula. 2 pi rm h. I need to remember that one because I don't think this. Oh shit. I don't think this is actually in her breakdown or our breakdown for formula sheet at all. I think this is a very special case for certain rotors or certain blades. I think this is for mean radius calculations, which is nice. Rearrange that. We get it in feet, turn it into inches. Boom, we have our blade height. I see why. Let's see, we found this. We know this. Or I mean, we know this, we know this. We found this, and we found this. Technically, it asks for this power first. But the thing to look for here is this conversion. Because if you just toss all that together, it's 30 times 0.24 times 6 times 143.6. 6203, and that's BTUs per second. And then you have to calculate it. Okay, that makes sense now. Change it from BTUs a second to horsepower. Because 1 BTU conversions was 778 foot-pound force. 778 foot pound force divided by BTU. But what that does is it gets rid of BTUs, BTU, and we're left with foot pound force. Then we have to one horsepower times foot pound force per second. 1 horsepower over foot pound force per second. So that should get rid of this second, this foot, this pound force, this foot, this pound force, this second. We're left with 1 horsepower. So you divide. Whoa. By the 550. That makes way more sense. But 778 divided by 550. That's where she gets that 1.14 right here. 8,700 horsepower. It's quite a lot. It's quite a lot. Dang. Lots of stuff, lots of stuff, lots of stuff. And prom's tomorrow. Okay, I am going to stream later this week after I'm all done and I've graduated, which is kind of cool. I'm going to set up my stream to watch my graduation, which is kind of cool. Ooh. But I want to make a plane. I want to make an RC plane. It's going to be 3D printed. It's got to be FPV. And it's got to be controlled by stick and throttle, not a remote control. Those are the 3 things I want to work on. 3 things. And I still want to look at some of the analytics of streaming on YouTube versus just making YouTube videos and then clipping out stuff. So we'll see. Okay. See ya. Over and out.